Hello learners of mathematics, welcome to session 5 for unit 6, algebra structures in the course Introduction to Abstract Algebra. So in the previous section, we learned about rings and its elementary properties. We did some fantastic proofs and interesting proofs over there. So in this section 5, we are looking at integral domains. I am Munkaila Tasmani, your course instructor. By the end of this session, you should be able to explain what an integral domain is. Give at least 2 examples of integral domains and then state and prove at least one property of integral domains. Okay, so commutative ring with identity. First, we will learn about commutative rings with unity and use that knowledge to explain integral domains. So we start with the commutative ring with identity. Suppose that addition and multiplication is defined on real number. Remember, then we say it's a group. Okay, so suppose you have addition. Oh, the addition is bent. Let me make it good. Addition and multiplication is defined on real number. It's a ring. Okay, so we have an element. 1 is a member of real, which you agree, and if there is also a in R, then what can we say? We can say that a dot 1 equals to 1 dot a, and that equals to a. So with unity that equals a, then we could say that the operation R plus is actually commutative ring. So any ring which satisfies addition and multiplication, which is defined on a real number, then we say that that operation is called commutative ring with identity or unity. So definition 7: if A and B are 2 elements of a ring R with A not equal to 0 and B not equal to 0, but AB equals 0, then A and B are called 0 divisors of the ring R. I think you are just agree with me, and that's very interesting. Once A is not equal to 0 and B is not equal to 0, but AB is equal to 0, then A and B are called 0 divisors of the ring R. Let's look at this. So the example 9 talk about multiplication modulo 6. So you can say that to multiplication modulo 6, you can say that 2 times 3 equals 0. But don't forget, but remember that theorem we talk about the modulo. 2 multiply 3 in modulo 6 is actually equal to 0. And so 2 and 3 are 0 divisors of multiplication modulo 6. 2 and 3 are actually 0 divisors of the modulo 6. Okay, so that's what we refer to that. Let's look at theorem 11. The left cancellation law states that, both the left and right cancellation law, which you are aware. So this is just a revision of the cancellation law. Maybe you can do it. So it's a. So when I have AB equals to BC, or let me say AC, so that it becomes very simple. AC, it implies that B equals to C. I hope you agree with me that, and that ends and we say right cancellation law. Note that A is not equal to 0. Right cancellation law. And also when you have BA equals to C, what can we say? B equals to C. And that is what? The left cancellation. So the cancellation laws are very, very, very important. The cancellation laws are very, very important. In all cases, A is not equal to 0. So you see the right cancellation, the left cancellation law, they are very important. Okay, so we are set to go. See, definition of integral domains. Okay, an integral domain, let me write because you don't have it here. So integral domain, let's say D, which with addition and operation, is a commutative ring with identity where 1 is not equal to 0. Okay, with no zero divisors. So that is for all A, B, be a member of the integral domain D with addition and then binary operation. Define AB equal to 0. So you can say that AB equals to 0. Once AB equals to 0 implies that either A equal to 0 or B equal to 0. Definitely one must be equal to 0. So either this equals 0 or 1 equals 0. So we normally use this idea to solve. Remember, use this idea to solve factorization approach when we are teaching your senior high student or junior high student. If you have AB equal to 0, multiplication law, either A equals 0 or B equals 0. One must actually be equal to 0. Okay, so that is actually definition of integral domain. So actually definition 8. So I've actually done the definition 8 over there. This is the definition 8. So what is the integral domain? Integral domain is an algebraic structure which incorporates one set with two binary operations. So you can see here, I should have asked you to explain. You can see one set and then we have the two binary operations. Okay, so integral domain is a structure which incorporates one set with two binary operations. So let me clean it so that it will come there for you to see. Okay, so I've already explained Theorem 8 or definition 8 for you. Okay, so I was explaining and then so it's here. So you can see them. So example 10, the set of integers and integral domain. Can we explain this? Explain to your colleagues. 2, if P is a prime number, then the ring prime numbers under integers is an integral domain. Prime numbers under integer is an integral domain. Just try to explain why are we saying that. Find more example in your material. Okay, axioms of integral domain. So here we have about a number of them. I'll try to set some few of them. The rest you can go through. An integral domain is an algebraic structure on which are defined two binary operations star and then the circle, which satisfy the following conditions. So the first condition is that it is closure under addition. And what do you say is closure under addition? If it's closure under addition, you can say that A star B is closed or is a member of D. Don't forget that your A and B are all members of D. So commutativity, associativity, they all hold, and I'm sure you know this thing. Very, very simple. Okay. Identity element for addition, that is 4. Identity element for addition. So you also know this, very simple. The inverse elements, okay, that's 5. The inverse element is also defined, and I'm sure you know this one. Then the closure under multiplication. So just if you have forgotten about them, check them in your course material. They are there. Okay, once you have associativity, they are also there. Associativity are also there. Very simple to show. Okay, and then you can talk about 8 products is distributive addition. We just look in the previous session. Number 9 is also commutative. Commutative is also commutative. So I can say that A operation B equals to B operation A for all A and B be a member of D. So simple. So simple. Okay, so and the next one, identity element for products and then non-zero element for all. Non-zero element for all. So just go through your course material. If I've forgotten about them, learn how to write them. Don't only state and write. Thank you. We don't want to make the video too long. Let's look at the properties of integral domain. Let D be an integral domain, then A dot B equals A dot C implies B equals A. Don't forget about your cancellation law. don't forget about your cancellation law. Okay, let me see if I can help you to prove this one some more with a not equal to 0. So let me help you to prove this small. So here, suppose that a dot b equals to a dot c. Suppose that a dot b equals a dot c. Then what do you have? I can have a dot b minus a dot c equals to 0, because I'm subtracting a dot c from both sides. And then I can also have, oh, there's a in both parts, so a dot bracket open b minus c, I hope you agree with me, equal to 0. And that is fine. We have here a is actually not equal to 0, implies that once a is actually not equal to 0, implies that b minus c equals to 0, because one of them must certainly be 0, and therefore we can say that b minus c equals to 0 implies b equals to c. Okay, because C, and that proves for that. So learn how to prove some of them. They are very, very interesting. Try to prove all. Okay, so prove this as an exercise. Prove that dB an integral domain, the b dot a equals to c dot a implies that b equals c. We are still proving around the cancellation laws.